So this will be the first of 4 presentations looking very briefly at climate change, and particularly climate change's synergy with energy and population. Because really climate change is a symptom of an energy problem. It's a very important symptom, and it's also a symptom of overconsumption and unsustainability, but nevertheless primarily climate change is caused by our choices of energy supply, most of which come from hydrocarbons right now. Fossil hydrocarbons that were buried millions of years ago and are now being released back into the atmosphere. This is a wonderful source of energy in terms of its concentrated nature, its portability, its convenience for developing a modern society, but it has this drawback that is increasingly becoming apparent, that when you release enough carbon into the atmosphere in the form of carbon dioxide and methane, you can have a major effect on the climate. Burning fossil fuels, such as coal especially, also releases many atmospheric pollutants that have a local effect that we would rather get rid of. In the broader context, the increases in greenhouse gases, which are illustrated over here, there's carbon dioxide, methane and nitrous oxide, which is one involved in agriculture, are very much in the context of rising everything. As the human population has grown, and I think Michael will talk more about this, our economic system has increased dramatically, and with that, a huge increase in our use of the resources of the planet. So this is obviously a problem if it goes on forever. Any ecologist will tell you that exponential growth eventually reaches a point of unsustainability, and in natural systems there's some equilibrium or a crash. That will happen eventually. Either we'll equilibrate in terms of our use of resources, or we will run into major problems. And it seems like that crunch point is approaching quite rapidly. In terms of carbon emissions, they are certainly showing no signs of declining. This graph shows emissions in the black line that have occurred since 1990, and the red and orange and other coloured lines are projections for future growth, but these are projections that were made 10 or so years ago, and the 2 red dots illustrate quite clearly that we're doing pretty well against the top end of those projections. So we're not slowing our growth of carbon emissions right now, but that will have to change very soon. Much of the growth in modern emissions is coming from the developing world. Most of the emissions that have occurred in the past have come from the developed world, so places such as the USA and United Kingdom, Germany, and even places like Australia. Most of the future emissions, and especially the growth in these, will come from China and India and other developing countries. And this graph just illustrates how rapidly the growth of carbon emissions is occurring in China. They're installing over 50 gigawatts of coal-fired power each year. Scientists from many disciplines are now increasingly understanding that this is causing a change in the climate. This is one illustration from the 4th assessment report of the Intergovernmental Panel on Climate Change, which is a review body that looks at the whole scope of scientific literature on climate change and synthesises this in a way that shows a big picture. Well, the big picture is that the temperature is going up, and many other features that respond to changing temperature, and indeed overall an increase in the amount of energy that the Earth is retaining, this is solar energy that it's retaining, is causing a change in the climate system that will eventually have profound consequences. I like to show this animation because it's an illustration of that previous slide, but shows how the climate can change over a century, but also it gives you a feel for year-to-year weather effects, where the blue is cooler periods, cooler areas compared to about mid-20th century, and yellow and red are warmer. So throughout much of the early 20th century, there wasn't a huge trend in temperature. It went up a little. It's really been since about the 1970s that we've seen a major change in temperature. This has always been a play-off between increases in pollution that cause cooling effects on the planet and CO2 that causes warming effects. But the warming effects of CO2 and other greenhouse gases is starting to predominate. That's 2007. You can see again an anomalously hot year, especially in the polar regions. That's a phenomenon known as polar amplification of the warming. Basically, as you warm the planet further, you get a retreat of snow and ice. It's formed for less of the year, and so you get more warming in those areas. This graph shows 2008, it's the best one I had for that year, compared to the average 2001 to 2007. 2008 was a slightly cooler year compared to the last few. It was a La Nina year, and the Pacific was particularly cold. A lot of cool water was brought up from deep in the ocean to the surface, whereas other areas such as the Arctic experienced their hottest year on record. So it was rather uneven. Overall, still almost half a degree above the average from 1951 to 1980. We've also seen something potentially more important in changes in air temperature, and that is a change in the heat content of the oceans, which is what this graph illustrates. We've only been able to measure that relatively precisely since about the 1970s, and since then we've seen a continued gain in energy content in the oceans. The oceans are a huge mass of water that takes a lot of energy to change their temperature at all. So most of the energy that's been caused by the increase in greenhouse gases, causing energy to be trapped at the surface, has gone into the oceans, perhaps around 90% of it. About 7% has gone into melting ice and snow, and the remainder, about 3%, changes air temperatures. So what happens in the oceans has a big effect on what happens on year-to-year temperatures, and it also illustrates the gain in heat of the planet. This shows sea surface temperature in the blue since 1990 through to 2008. You can see there's the trend upwards. There's some hot years and some cooler years. This is the solar cycle, which goes about every 11 years. We're in a deep solar minimum right now. Has some effect on the climate. This has a stronger effect, at least in the short term, and this is the ENSO, the El Nino Southern Oscillation, where you get El Nino years such as 1998 and a patch of El Nino years in the last few years. You get warmer temperatures. La Nina years such as there and 2008, you get slightly cooler temperatures. Those short-term fluctuations in weather and regional climate can be largely explained by these non-trending phenomenon. The trending phenomenon, the increase in greenhouse gases, has that overall effect of pushing the climate system in a particular direction. Greenhouse gases push it towards a warmer condition, and other effects such as aerosols, dust and sulfates and other low-lying pollutants that we throw up in the atmosphere have a net effect of cooling the atmosphere. But we're pretty uncertain about just how much and per metre squared. Aerosols cool the planet, greenhouse gases warm the planet. We're much surer about how much greenhouse gases warm the planet than we are about the aerosol cooling. But you integrate those two distributions and you get the net forcing, somewhere between 0 and 3 watts per metre squared, with a best estimate of about 1.5. Now we can plug that sort of information into quite complex computer models that obviously do a lot more than simply look at concentrations of a few gases and aerosols. And we can use those to simulate the climate, and they're used to make future projections. Ideally, if we wanted to understand the relative effects of people, we'd conduct experiments on multiple Earths, but we can't do that. So in the absence of that, we have to create simulated Earths and conduct these sort of experiments. That's what the bottom graph illustrates. The black line is the historical temperature change, and the pink is model runs that include all of the effects we think affects the climate. Answer effects, forcing effects such as volcanoes and the sun, and changes in ocean heat content and so on. Now what you can see quite clearly is that there's very little to tell between human and natural effects through to about 1960. But there's a large divergence after that. We would expect a slight cooling of the planet. We've instead seen a warming of about 0.6 of a degree. That gap is the human fingerprint on the climate. Now we can use those models to make future projections about climate change, but they are underpinned primarily by scenarios of future changes in carbon emissions. If we're able to mitigate our carbon emissions dramatically, or if we run out of hydrocarbons, we'll follow the lower storylines, and if we continue business as usual and we continue to extract hydrocarbons, we'll follow the upper scenario. So anywhere from 2 to 7+ degrees of warming this century, where 2 degrees of warming itself represents a massive shift in the climate system, because it's not like the change in weather. It's actually an index of the state of the planetary climate system, and a 2 degree shift will have profound consequences.